What's up? I'm back again to do more topic revision introduction. Right, now that we've got the introduction over, today we're going to talk about physics. Space physics. Space is one of my favourite topics because it's interesting. You know, space, the final frontier. These are the voyages of the Starship Enterprise on its 5-year mission to seek out. But we're going to cover space because space. Let's start off with the first thing we're going to cover. Stars. You know, the big ball of burning in the sky, really far away in one direction, and it burns. Nuclear fusion. With stars, they obviously have a life cycle. Where they came from, where they'll end, and where they are currently. Now, let's have a look at that. So, we're going to start off with a nebula. We all know what nebulas are, and if you don't, they're basically just gas in space. Just a big cloud of gas. Nebula is just gas. Moving on, from a nebula, we have gravity. Even though gas, it's really small particles, it still has gravity. Everything has gravity. I have gravity. This wall, it has gravity, it's just so weak we can't really feel it. But yeah, in a nebula, the gravity will affect the gas, probably hydrogen I'd say, just because hydrogen. It will pull it together, then more will get pulled together, and eventually clump into a big ball of hydrogen, and after a lot of intense pressure, push together due to gravity and all that stuff, and heat and etc., it will start nuclear fusion. Hydrogen will go into helium. Anyway, when that happens, okay, the star will shine for the first time. It's called a protostar. But yeah, this protostar will carry on gathering, more and more and more hydrogen, fuse it to helium and expand with outward pressure. But as it expands, the gravity is going to get stronger. And as the outward pressure equalizes with the force of gravity, it stabilizes. And this is what we call a main sequence star. Now, our sun is a main sequence star. You can probably tell because it's, keeping us alive. And it's stable. Henceforth, a main sequence star. Once you have a main sequence star, a normal sized star, like our sun, will go a very different route to what a large star would go. So there's two separate ways in which they go. I'm going to cover what a star like our sun will go through first. After it's been fusing, hydrogen together, making helium and whatnot, for a while, just slapping them together under intense pressure. After it's done that for a while, it will eventually run out of hydrogen, right? Once that happens, it will turn into a red giant. Yeah, red giant, exactly. Now, a red giant is basically, there's a name, it's red and it's giant. A red giant is basically capable of fusing heavier elements such as helium into heavier and heavier elements. Of course there is a limit though. Once that happens though, it just expands because the outward pressure from the fusion is stronger than the force of gravity and it expands once again. And eventually the outward pressure though is strong. It'll be stronger than the gravity, so it'll carry on expanding. But eventually, it will be so much stronger than the gravity, its layers will just float away. Because that's what happens. It just floats away. So once all the layers are gone, you're left with a glowing core. This core is called a white dwarf. Now, after, so many years, that white dwarf will cool and will become a black dwarf. And that's how normal stars end. That's the life cycle of normal stars. Now, large stars, however, starts off basically the same, probably with bigger amounts of stuff involved, but once it runs out of hydrogen, it will go into a red supergiant. hence the name red supergiant, because it's a red supergiant. It's super and it's giant and it's red. That's why it's called a red supergiant. I actually have a favourite star called Betelgeuse. That's a red supergiant. It's Orion's left shoulder, I think. You know, the constellation, Orion's belt, and all that. Astronomy. Anyway, a red supergiant. Alright, it's bigger than a red giant, hence the super in it. And eventually, what will happen with a red supergiant is that it can actually fuse elements up to iron. Okay, it's up to iron. That's how heavier elements are formed. But up to iron, it kind of stops there. So to get heavier elements than that, the star has to explode, and it explodes when it explodes. Yeah, well, when a red supergiant explodes, it's called a supernova. You know, a big explosion of stuff. And in this explosion, there is so much force and pressure and all that involved, it can fuse heavier elements than iron. So that's where we get heavier elements from. But after a supernova has happened, it can leave two different things behind from a red supergiant. A neutron star and a black hole. And we all love black holes, don't we? Yeah. You know, the thing that could spaghettify you to death and slow down time and all that lovely jubbly stuff. Event horizons, Hawking radiation, etc, 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 etc. Anyway, that's the life cycle of a star. Now, that's not it. Space, vast, and it's big, and it's empty. But with space, you have gravity and the effects of gravity. Now, of course, gravity exists. Otherwise, if I jumped up, I would just hit my head on the ceiling. Gravity is generally credited to Isaac Newton. There are many different theories. The story says an apple landed on his head. Another story says he saw an apple get pulled by the wind and it took longer to hit the floor. And he came up with an idea of orbits there. But generally those are different ideas of how Isaac Newton came up with gravity. But what we're talking about is talking about orbits. Now, with orbits, it's essentially an object falling. That's literally what orbits are. If you go into orbit, you're essentially just falling down, but also you're going horizontally, so you're constantly falling around an object. With an orbit, since it's constantly falling and constantly going around, it means that it's constantly accelerating and changing velocity, but it's not changing speed, because, it's a different vector and all that. But anyway, yeah, it's not changing speed. So that means if the speed were to change in an orbit, the radius of the orbit would have to change in order... The reason why speed doesn't change is because the radius would have to change to maintain a stable orbit. Actually, fun facts about stable orbits. Our moon is in a degrading orbit. Believe it or not, it's too fast. So every passing year it gets further and further away. It's very slowly, sure, so we're not going to see it disappear in our lifetime, but it's still moving very, very slowly out because it's too fast for its orbit. Fun fact. We're going to lose our moon someday, unless we do something about it. Moving on to the universe. Insert echoing effect here. The universe is big. Very big, in fact. So big, we don't know how big it is. To the point that it's just forever expanding, changing shape, whatever shape that may be, if it can even be considered a shape. Aha! Space. There are many theories of how it came to be, but the main one is the Big Bang Theory. Now, I'm not talking about the show, I'm talking about the scientific theorem, or theory, or whatever you want to call it. Basically, this states that there was a singular point of infinitely dense and infinitely hot matter that one day just decided to go kaboom. That's literally it. One day it just decided to go kaboom and expanded out, and that's how the universe was born, and it's still expanding to this day. Now, there are actually two juicy bits of evidence for the Big Bang, which I'll dive right into about now. But it is really cold in here, so I'm going to go and warm myself up next to this radiator. I'll be back in just a sec. I'm back again. I've already used that in a previous video. Now into those two juicy bits of evidence for the big kablooey. Okay? Now, the first bit of evidence is the red shift. Now, what the red shift is now, what the red shift is, it's basically a shifting into red of light. Because when we look at distant galaxies, they are moving away, okay? And then the light is coming towards us. We observe that light, and it shifts into the red spectrum. Now, this is because red is a longer light wave than, let's say, blue. So, since it's moving away, the light wave kind of stretches, if that makes any sense, to red. It kind of shifts into red, hence red shift. Now, if you know what the Doppler effect is, where sound waves kind of compress and depress, is that the correct word? That's why you kind of get the meow sound effect of a car, because of the... It's sort of like that, but with light in the galaxy moving away. No, that's how I think of it anyway. But yeah, the red shift, it provides evidence for the Big Bang, because, well, the galaxies are moving away, and they have to be moving, since they're moving, they must be moving due to some cause. Physics. The second bit of juicy information to prove the Big Bang is CMBR, or Cosmic Microwave Background Radiation. What this background radiation is its background radiation from when the Big Bang decided to bang. What it is, it's been bouncing about the universe for such, and wherever you look, it's exactly the same. Now, we discovered this, humans as a species, discovered it when two people, I forgot their name, I think it's something like Perez and Fernando or something. I will be back in just a minute. The people who discovered cosmic microwave background radiation was Penzias and Wilson. Basically, they were trying to completely free up or completely isolate a microwave receiver, but they couldn't. They kept on getting this background noise. Funny story, actually. Since they used a big cone contraption to capture the microwaves, birds were nesting in it, and they thought birds were causing the interference. But no! It was cosmic microwave background radiation! These guys were like, hang on a minute, why do we keep on getting this interference? We've tried to clear out the cone, and we've done all this and this and this, and basically they came to the conclusion that it was cosmic microwave background radiation. Of course, they did a lot of other tests to come to that conclusion, but they came to the conclusion nevertheless. Now, as I said, this proves, it provides evidence for the Big Bang, because it's the same everywhere you go. It has the same signature, frequency, etc., etc. Okay? So, yeah, literally everywhere. You could go, hop over to the next galaxy, it'd be the same over there. You can hop over to the next solar system, same there. Head all the way over to the neighbouring stuff, same, completely everywhere. Anyway, that basically covers everything in the space topic. I want to say everything. There are a few bits and bobs here and there that I haven't covered, but yeah, I hope you guys have enjoyed this video, because I enjoy space a lot, and I enjoy talking about it, and I just enjoy it in general. As you can tell by my anecdote earlier about Orion's shoulder being my favourite star, Betelgeuse, the red supergiant, that could go supernova any day now. I'm not even joking about that. Literally, like, a couple of years from now, we could look into the sky and just see Orion's shoulders just all over the place. And yes, the sound effects were extremely necessary. I'm ending the video here. I hope you guys have enjoyed this video. I hope you guys have learned something, or finalised something, whatever. I just don't care at this point. I'm just going to end the video.